Can a small, local AI model sort through my emails and tell me what actually needs my attention? This is what I'm testing in this video. I want to see how far I can get with a small, local model running on an average computer connected to real or test email-shaped data. I'm Kristen, I'm a software engineer, and this series is less of a traditional coding tutorial and more of a systems design experiment. I've worked with cloud AI models in production systems before, but I've also been really curious about local models. What they can actually do, where they hit their limits, and what kind of structure they need to become useful. I learn best by building, so this series is me testing that in public. I'm building small local AI agent workflows, reporting what works, what fails, and what I would change next time. In this video, I'm starting with communication triage. Can a small local model sort through email, identify what needs attention, and create structured outputs the next part of the assistant can use? This is the first module in a larger executive assistant build. Part 1 is communication triage. Can the assistant sort through messages and create a useful briefing? Part 2 will be calendar management. That is where action items can become tasks, and tasks can be placed into open time blocks. Part 3 will be meeting prep. This is where the assistant can look at upcoming meetings and pull together relevant context. This is where I will start adding memory. If the experiment keeps holding up, I'll keep adding layers: meeting prep, research workflow, and smarter communication. In this video, I'm going to break the experiment into 3 parts. First, I'll build the communication triage pipeline with the test data, so the data flow is easy to see. And then I'll swap in real Gmail data, because real email is much messier than clean test data. And at the end, I'll use the same pipeline to test different models, local Llama models and Gemini for a baseline, so I can compare speed, schema reliability, and output quality. Here's the high-level flow for this first module. The app starts with email-shaped JSON files in data/inbox. Each message has the same basic shape. This is important because the processor should not care where the message came from. The connector's job is just to normalize the raw data into the shared shape. Next, those messages get loaded by main.py. Main.py is the coordinator. It does not classify emails directly, and it does not talk to the model directly. It calls the pieces that do the jobs and makes sure the full flow runs in the right order. I am also using main.py to make the experiment measurable. Every major step prints to the terminal, and I'm timing the Gmail pull, the summary process, and the full run. That way I'm not just guessing whether a change helped. I can compare the actual runtime across dummy data, real Gmail data, local models, and Gemini. Then the messages go into communication summary processor.py, which is where most of the triage logic sits. I'll break down the individual functions as the video progresses, but at a high level, this file is responsible for preparing the messages for the model, building the prompt, sending each batch to the model, parsing the JSON response, and merging the results back into one final summary. After the processor builds the prompt, sends the message batch to Qwen through Ollama, agent.py is where the code talks to Ollama. Once the model returns structured JSON, Python can use that output in 2 ways. The first path is the human-readable briefing. Markdown writer.py turns the structured results into a daily communication summary. The second path is the action handoff files. Action exports.py takes the same structured result and creates files for reply drafts, to-do-ready items, follow-ups, and waiting on tracking. So the model is not responsible for writing every final file by itself. The model classifies, Python formats, and routes the result. Before I tested this on real email, I started this with 3 simple test messages. The first big lesson was prompt structure. When I originally started this, I had a structured Markdown prompt. I told the model to create a communication summary with sections like important messages, messages that may need a reply, follow-up items. That prompt was not terrible. It was much better than just saying summarize these emails. I also purposely left JSON false in a vague system prompt to show what happens. But it still had problems. It was human readable, but not agent ready. Sometimes the model added thinking, sometimes it organized things in a fuzzy way. So I changed the prompt file from write me a summary to classify each message into exactly one category and return valid JSON. That change was important because summarized messages is no longer just asking for a nice response. It's expecting structured data that Python can parse, merge, and send to the next step. The other change I made was adding a strict JSON system prompt and turning on JSON mode. The prompt file tells the model what categories I want, but the system prompt reinforces that behavior. Then setting JSON mode true tells the model call that this response needs to stay machine readable. Here is the structured JSON output from the updated prompt. This was the first version that felt agent ready instead of just human readable. The model returned the categories my code expected, and Python could parse the result instead of trying to interpret a Markdown summary. In this test, the improved prompt also completed much faster. It went from 87 seconds down to 27 seconds. I don't want to overclaim that the prompt alone caused all of that, because local model timing can vary. But the stricter prompt likely helped because the model had less room to ramble. Instead of writing a loose summary or reasoning through the task, it had one job: return valid JSON in the exact structure I asked for. Now that the prompt is returning structured JSON, the next question is whether the local model can return that JSON reliably and quickly. This happens inside the model call in summarize messages. This is where the processor sends the finished prompt to my model wrapper and passes the settings I want to test. NumPredict controls how much the model is allowed to write back. It is the output limit. If it's too low, the model may start the correct JSON but get cut off before it finishes. With a small 3-email test, I intentionally set NumPredict too low. The model understood the assignment and started returning the right JSON, but the output got cut off before it finished. Python threw a JSON parsing error because the response was incomplete. That was a useful failure. The model did not misunderstand the task. I simply did not give it enough output room. Then I raised NumPredict to a working value, and the JSON completed successfully. The key lesson is that NumPredict is not a make it smarter setting, it's a maximum output limit. Too low and the output can get cut off, high enough and the model has room to finish. Higher than needed does not force the model to write more, especially with a strict JSON prompt, but with a loose prompt it can give the model more room to ramble. NumCTX controls how much input context the model can hold in view. That includes the system prompt, the triage prompt, the JSON schema, the category rules, and the actual email messages. When NumCTX was too low, the model did not just cut off, it lost the assignment. Instead of returning the triage JSON, it started echoing the input message back to me, and even repeated part of the newsletter text over and over. That is a different failure mode from NumPredict. When NumPredict is too low, the model may start the right answer, but run out of output space. When NumCTX is too low, the model may lose the instructions, miss the schema, ignore the rules, or behave strangely because it cannot hold the full prompt and message content together. When I raised the CTX, everything ran as expected. So the simple way I'm thinking about it is NumPredict is output room, NumCTX is input room. The 3-email test worked, but real inboxes are not predictable. Some days there might be 3 messages, other days there might be 27, 50, or more. So the next test was sending 27 messages in one request. That failed in a different way. The model did not return before Python's timeout. The error was read timeout from the local Llama request. That means Python waited for the model, but after the timeout limit, it gave up. I tried raising NumPredict in NumCTX, but still get a fail. That was the clue this was no longer just a tuning problem. It was an architecture problem, and also a small model limitation. A smaller local model can do useful work, but it needs the work broken into manageable pieces. I could keep making Python wait longer, but that does not make the local model faster. The better solution is batching. Batching means I split the inbox into smaller chunks. Instead of sending 27 messages in one giant request, I send 5 messages at a time. Each batch is smaller, each output is more predictable, and Python can merge the structured JSON results after the batch. And so the flow becomes load all messages, split them into batches, classify each batch, collect the JSON result, merge them into one final summary, and then create the briefing and handoff files. Once I had batching, the next natural question was, can I process more than one batch at a time? In normal API work, threading can help because your code is often waiting on another server. The remote service might have many workers, servers, or infrastructure behind it. But with a local model, my computer is the server. So when I tried threaded batching, the batches were competing for the same local CPU, memory, and Ollama process. The threaded version technically worked, but it barely improved runtime. In my test, the sequential version and threaded version were almost the same. And that makes sense. Python was not mostly waiting on a separate external system. The bottleneck was local model generation. So for the default version, I'm keeping sequential batching because it's simpler, it's easier to debug, and nearly the same speed on this machine. Once batching worked, the next step was making the structured JSON useful. The model returns categories, but those categories need to turn into something I can actually use. So I added 2 output paths. The first is the human briefing. That's the Markdown email style summary I would actually read. The point is not to summarize the entire inbox. The point is to reduce the inbox noise to what needs attention. The second is the action handoff. And these are separate JSON files that future connectors can use. The first handoff file is reply drafts.json. This comes from needs reply. These are the messages where I should probably respond to the sender. For example, if a client asks whether the first draft will still be ready by Friday, that becomes a reply draft request. Right now, the agent is only preparing the intent for a future draft connector. It is not writing the final email, and it's definitely not sending anything. The reason I'm stopping here is that good reply drafting needs more context than just one incoming email. Before I want the assistant drafting responses, I want it to understand my tasks, my calendar, recent decisions, meeting notes, and maybe even previous messages in the thread. So I'm going to come back to this in a few videos after the assistant has more memory and context. The second handoff file is to-do items JSON. This comes from both needs action and follow-up. A needs action item is something that should be handled now or soon. A follow-up is something that should come back later. So both can be to-do ready items, but I label the type as either action or follow-up. I also added do hint and priority hint. If the email says by Monday, in 3 days, next week, or after lunch, the model should keep that timing phrase as a do hint. I'm not asking it to calculate real dates yet. That will belong in the to-do and calendar module in the next video. The third handoff file is waiting on items.json. Waiting on has a very specific meaning. It means someone else has the next move. This category will become more powerful later, especially when I start pulling sent mail and full email threads. For now, it gives me a place to track open loops where I'm not the next person who needs to act. Once I added the handoff files, I started seeing the next big lesson. Real triage needs rules. The model can identify possible actions, but I still have to define what actually counts as action. For example, the model treated a productivity newsletter as a follow-up. That is wrong. A newsletter is not a follow-up unless it clearly asks me to do something. It also treated a lead asking for a call as a follow-up. But a real person asking a direct question needs to be a reply. And it treated some meeting reminders as waiting on. But a meeting reminder is not waiting on. Waiting on means someone else has the next move. After the test data worked, I swapped in real Gmail data. I'm not making this video into a full Gmail API tutorial. The important part is that the Gmail connector pulls the messages and normalizes them into the same message shape as my test data. That means once the real email data looks like the test email data, the rest of the agent does not need to change. But the first real Gmail run exposed a new problem. Real email is much messier than test data. The first time I ran it, the local model timed out. And when I looked at the raw Gmail output, it made sense. One newsletter could contain thousands of characters of tracking links, image labels, unsubscribed text, social links, legal footers, and repeated marketing sections. So I added a cleanup step in a new email cleaner file. Then I added another filter because I realized it's not even worth spending local model time on obvious newsletters, promos, recommendations, or low-value automated emails. So the connector is doing more than just pulling Gmail now. It's cleaning and filtering the inbox before Qwen ever sees it. That made a big difference in the real Gmail run. It pulled 20 messages, skipped 14, likely low-value messages, and only sent 6 messages to the model. After running it through, the total time took 593 seconds. And for a small local model, that cleanup step matters a lot. I don't want the model spending 5 minutes reading newsletter footers when the real assistant task is figuring out what actually needs my attention. Once the pipeline was working, I wanted to test one more question. Is Qwen the best local model for this job? Or do different small models handle the same task differently? I tested Gemini first as a cloud benchmark, just to see how fast the same workflow could run with a hosted model. As expected, it was significantly faster. The full process took 14 seconds. Then I switched back to Ollama, and I tested a few local models. This is where the experiment became more interesting, because speed was not the only thing that mattered. Then I tested Qwen 3 1.7b. This model was lighter than Qwen 3 4b, and some batches did run faster, but it failed the assignment. Instead of returning the exact schema my code expected, needs reply, needs action, waiting on follow-up and FYI, it created its own structure with keys like sentiment and keywords. This was a useful failure because it showed me that smaller is not automatically better. If the model cannot follow the output contract, the rest of the app cannot reliably use the result. Next, I tested Llama 3.2 3b. This was a better result. It completed the full pipeline, followed the required JSON schema, and was faster than Qwen 3 4b. The full summary took around 7 minutes and 53 seconds. Then I tested Gemma 3 4b. This was the strongest local result so far. It completed the full pipeline, followed the required JSON schema, and was the fastest local model I tested. The summary took about 409 seconds, or close to 7 minutes. This is still much slower than Gemini, but for the local experiment, it was the best balance so far. The takeaway from this model comparison is that the best model is not just the fastest model. For an agent workflow, the model has to follow the assignment, it has to return the right structure, not just a plausible answer. For this communication triage task, Gemma 3 is probably the local model I'll use as my default going forward. But I'm going to keep comparing models at the end of future videos because this opens up another question. Do different small models perform better at different assignment tasks? At this point, part 1 has a working communication triage layer. It can load email-shaped data, classify messages in batches, return structured JSON, create a human-readable briefing, and prepare handoff files for future modules. So, coming back to the hypothesis for this series, can a small local AI model handle useful work tasks on a regular laptop when it has clear inputs, tight limits, and controlled access to data? After this first communication triage experiment, I would say yes, but with trade-offs. Local processing was significantly slower than cloud AI, and real email needed cleanup, filtering, and batching before it became manageable. This is obviously not the speed I would expect from a production system. But for someone who wants more privacy, lower cost, and local control, a background agent that runs once or twice a day on your own computer could still be useful, even if it takes several minutes to finish. The key takeaway is that the small local models can do real work, but the surrounding system matters. This is also where I'd love discussion from people who are experimenting with local AI. If you have a model you think I should try, a better way to structure the prompt, or an optimization that might make the local AI run faster, leave it in the comments. I might make a future video testing viewer suggestions. In the next part, I want to move into calendar management. The to-do items.json file becomes the bridge. Needs action and follow-up items can become tasks. Then the calendar module can look at my day, find open blocks, and suggest where those tasks should go. Before I let the assistant move or schedule anything, I want it to understand the day first. So the next experiment will start with calendar debriefing, then move into time blocking. And that's it for today. Thank you for following along. I'll see you in part 2.